Welcome to the lecture on sustainability in production and consumption. We want to first cover the difference between production-based or country-based accounting and supply chain-based accounting of emissions. Then we want to learn something about the difference between environmental and ecological footprints, and finally give an outlook on how to reach sustainability in production and consumption, which is one of the Sustainable Development Goals. Most commonly, emissions are accounted for where they occur. That's very natural because regions have the legislative power to do something about emissions within the territory, so we can just calculate all emissions together from traffic, from industry and the other sectors, and then try to understand how it evolves over time and make a policy for it. And also the emissions reduction targets are all based on territory-based emissions. Here's an example for Germany where we can see how the country's emissions, so all emissions that happen within the territorial boundaries, changed over time. So in the 90s until 2005 there was a steep decline, mainly because of offshoring of industry and phase out of coal as major energy carrier. Then we have seen a stable plateau, and in recent years, due to the transition to solar and wind electricity, emissions started declining again. And the target for 2030 would be a 55% reduction, and of course there we still have a long way to go. So change is happening, positive change is happening. Whether it's enough, well, this is a different debate, but you can see that emissions accounting at the country level helps to both understand what's going on within the country, the different sectors, and also how the national emissions inventory relates to a climate target. At the more detailed level, we see that even though there's lots of sustainable development happening in Germany, some incentives are still misplaced. Here, there's an overview of the carbon intensity of different fuels. This is the blue column with the legend on the left side, carbon intensity in grams of CO2 equivalents per kilowatt hour of energy carrier. And on the right side, the green bars, we have the energy tax in euro cent per kilowatt hour. And you see there's not much correlation. We have a huge energy tax on gasoline, which is traditionally the case because we use this gasoline tax revenue to finance the road system. And also the demand for gasoline is very inelastic, so we can tax it a lot and people will still continue driving their cars. On the other hand, coal, which is a very polluting and climate unfriendly energy carrier, has almost no energy tax in relative terms. So you can see that the tax system we have is labeled eco tax or sustainability tax, but the actual tax levels are a legacy of previously incumbent fossil fuel based economy. And if you want to really adjust these energies taxes right to also reflect the climate impact, which they're supposed to do, there's still a long way to go on the policy side. Another way of looking at it at the territorial side is here to again list the different energy carrier and then calculate how much the energy tax accounts for in terms of the total price. So this would be the first column here on the left with numbers. So you can see that for gasoline and diesel, so the private transportation fuels, roughly half of the price we pay is tax load. But for natural gas, private, it's much less, it's only 9%, and coal, the industrial coal users would only pay 18% of that coal price as energy tax. And then we can also calculate how much the current energy tax rate corresponds in terms of carbon price. We do this by dividing the two values from the last slide, the tax load per kilowatt hour divided by the carbon per kilowatt hour, and then we get, so to say, the virtual carbon price or the energy tax per CO2 that's currently already paid. And for diesel and gasoline, this is more than 150 euros per ton, so we have already a very high energy tax load compared to the carbon. But for other fuels, it's much less, like ridiculously low again for coal, where the energy tax is almost nothing, and also compared to carbon is almost nothing. And if we would now, on top of what we already have, add 100 euro per CO ton carbon tax that comes on top of everything else, we would see, of course, that the prices of the commodities change, But again, because gasoline and diesel are taxed already very highly, there's not going to be much change. So again, demand won't react much to that, but other energy carriers, especially coal, would increase in price a lot. So you can still see for sustainability transition there's a lot of way to go, and substantial price increases are needed to install the price signals that also these high carbon fuels are used to a lower extent. So the accounts we have seen today can be done by looking at the fuels themselves or at the emissions in the territory. So this is the direct accounting, taking the fuel, taking the national inventory and so on. Another perspective that is also commonly applied is the footprint perspective. So here we want to see not only the emission intensity of the fuel when it's combusted or the production emissions in a certain country, but actually consider the whole supply chain. So for fuel, that would mean also including the emissions from the mining and drilling operations and refining operations, and for a country it would mean to also include the emissions that happen elsewhere to produce the imported goods for that country. So this supply chain or cradle to gate perspective is then embodied in the footprint concept. The environmental footprints can be calculated for many different so-called extensions. We would use multi-regional input-output models to do that, and these multi-regional output models then have certain environmental extensions. One, for example, for greenhouse gas emissions. Also common are extensions for land use, water use, and material use, and with those extensions we can then calculate the so-called embodied emissions or embodied resources in a certain unit of consumption. And the Industrial Ecology Open Online course has a section on supply chain assessment and especially multi-regional input-output model and life cycle assessment, where the technicalities of these calculations are explained in detail. The results are quite interesting. Here for the EU, you can see on the left side a difference between territorial and consumption-based accounting. So the left bar here tells you the emissions within the EU in the year 2011 in the different sectors. So these are the territorial emissions happening in those sectors. They are at roughly 4,700 megatons. And then the second column to the left are the emissions that are embodied in exports. So these are emissions that happen within the EU, but they are attributed to consumption in other regions because the goods are eventually exported to other regions. So this can be calculated also with the footprint approach. And then the second column from the right are the emissions embodied in imports. So these are emissions that happen outside the EU, but are included in the supply chain of the products that are consumed by EU citizens. So the two left bars are territorial emissions in the EU that are then partly reallocated to other countries. The second column from the left side is emissions in other countries that are allocated to EU consumers. And then the sum of the three, this is the right column, is the consumption-based account. So this is a mix of emissions in the EU and outside the EU that have a common feature, which is that they all appear in the supply chain of the consumption of EU citizens. So this is what we call the consumption-based account. EU citizens consume, EU institutions consume, capital formation and so on, and all these accumulated supply chain carbon emissions are then accounted for here. And you can see it's about 25% larger than the territorial emissions. The EU is what we call a net importer of embodied carbon. But of course the carbon is not actually imported, it's only the commodities that are imported, and the carbon is then emitted in the supply chain. And you can also see, here's an example for Germany on the right side, where those emissions end up. There's of course consumption very large, so all the commodities that we consume, that's 4.5 tons. We have food with 1.7 tons, we have mobility with more than 2 tons, and also our own energy used in buildings, electricity and heating, blue and red here, with together roughly 2.5 tons. An even more drastic change here is for the land and water footprint. So it's land on the left and water on the right, where we have the same plot structure as above, but the results are different. The EU is a net user of foreign land, And the EU land footprint is 80% higher than the EU own land that it's used within its territory. And for water, the footprint is even higher. The total water footprint is 2.5 times the domestic water footprint. And important to understand here is that the land we're talking is actual physical land. So what we do here is we take the land, for example, for soy production in Brazil, or for wood production, timber production in Russia. And if the soy and the timber ends up in products that are eventually consumed in the US, in the EU, the land would be allocated to the EU. So the land we're talking about is actual arable land, pasture or forestry that is used. It's actually used to satisfy EU final consumption, so it's not available to other people. So it's actually physical constraints we're talking about here. And what we can do now, this is an example for Germany, we can take those footprints, because we say, well, the footprint is a measure of the resources that are needed to supply a certain commodity. It doesn't matter where on the earth it works or it's used, but it's necessary to produce a certain commodity. So we can take those footprints and we can upscale them, assuming what would happen if everybody on this planet would on average have the same footprint as the average German. So we have in the unit that are given here, the Germany total footprint. This is then for the total population. We scale it up to the world population, and then at the world level we can compare the footprints to the planetary boundaries, the biophysical boundaries for greenhouse gases, for arable land, for water use, and we can see how an upscaled footprint relates to the planetary boundaries. And what we see is that for climate change and greenhouse gas emissions we are way above the target, maybe a factor of 10. Depends on how we calculate the budget, but it's clear that the footprint, the carbon footprint of Germans and of most other people in high-income countries is way above the global limit. And interestingly, also the arable land footprint is above the limit, and this is of course a consequence of the high meat consumption. So 40% exceedance of arable land. It means simply we cannot scale up this lifestyle we have to the global level. There's not enough arable land, and also the land boundary would then be exceeded. At the average level or aggregate level at least, it seems like that for water and total land we are still below the boundary, but again that doesn't mean that there are no local hotspots in the supply chain. The carbon footprint problem is pervasive, and here's an example of the tourism sector where Lenzen and colleagues have estimated that roughly 8% of global greenhouse gas emissions can be attributed to tourism. And this is of course not directly sector-wise, but this is supply chain-wise. So a lot of accommodation, a lot of transport, and also a lot of retail services, hotels and restaurants and so on can be allocated to tourism activities, other than business activities, for example. And overall, the supply chain carbon emissions of all tourism activities can be as high as 4 gigatons, which is again quite high, and also shows the importance of high affluence and the relevance of high affluence in also carbon emissions and allocating carbon emissions to end-use consumption. A tricky part of the carbon footprint picture is that we see as people get richer, their footprints tend to increase. So far, there's very few examples where higher income also leads to lower footprints. And this is, of course, a major problem because the footprints are actual emissions, right? And they need to be reduced. But we see that the footprints increase with affluence. So even though some countries manage to reduce their domestic emissions, it appears that most of their consumption-based emissions still increase with rising income. And since rising income is still the main column or the main pillar of economic development policy, we have really a deep contradiction here in our economic system. The need to reduce emissions on one side, but then the strong coupling of emissions footprint to rising incomes on the other hand. So that is a very strong finding that has been repeated multiple times, and it means that eventually we will really need to rethink our relation between production, consumption, and sustainability and well-being. When we reallocate global resource use to consumption unit, we realize that the high-income countries use an over-proportional share of global resources for their own consumption. So because we have many resource extraction and emissions in poorer countries that are reallocated to consumption-rich countries because they're part of the supply chain there with the carbon perspective, footprint perspective, we see that the inequality in resource use and resource allocation actually gets worse. And that again means that because our current lifestyle is globally already unsustainable, the lifestyle of the people in the high-income countries is even more unsustainable than it seems like from looking only at country-based emissions. So this is again a huge problem, the strong coupling between resource use and the lifestyle in high-consuming cultures. There's a number of items that we can address where we want to compare the production country-based and the consumption-based emissions. So this is here for your reading. And this is of course important to understand what it's applied for, a few examples I just gave, and also what the uncertainty is and how easy it is to account for or calculate such emissions inventories. Again, the main difference is that the country-based emissions are used to benchmark countries and also to set national climate targets for, and the consumption-based accounts are used for quantifying the lifestyle impacts on carbon and other natural resources. We talked about footprints a lot, and there is the well-known ecological footprint. And here I want to quickly explain the difference between the footprints that I just talked about, the environmental footprints, and the ecological footprint. Essentially, the ecological footprint is an aggregate footprint indicator that takes different environmental footprints and calculates them all into a common unit, a land unit, that can then give an aggregate measure on a consumption unit's different footprints. So when you have consumption unit, you calculate its carbon footprint and its land footprint and its resource footprint. You can aggregate those footprints into a common denominator. How is this done? Well, for land footprint, it's easy because it has already the unit land. For carbon footprint, it is assumed that a certain amount of carbon can be sequestered on a certain forest area. So you would convert carbon emissions into forest area depending on where the forest is, and then have a land conversion factor. Similar for resource use, you in principle can say, okay, for this resource extraction we need so much mining area, so we can also convert resources into land footprints. So when we do that, we get an aggregate indicator that has one common unit that's called global hectares. In this indicator can be broken down into different categories. So we have the built-up land, forest land, we have grazing land and cropland, and the blue component here, which is the one that's most dynamic, is the contribution of carbon emissions to the ecological land footprint. So here again it's calculated that the carbon emissions would be sequestered in a certain forest area. Very importantly, the ecological footprint is a counterfactual indicator, because we know that in reality our carbon emissions are only partly sequestered by forests, but most of them stay either in the atmosphere or partly in the oceans. So it's a counterfactual indicator that calculates the virtual land or the hypothetical land that would be needed to sequester all of our emissions. And sometimes you hear that on average we need 1.5 Earth planets to account for or to compensate for our environmental damage, and the US would need 4 planets and so on. And this is of course a direct consequence that the ecological footprint of mankind is larger than the land we have, because we don't have enough forests to compensate for all emissions or to sequester all emissions, because they actually stay in the ocean and in the atmosphere. So there is some criticism to the ecological footprint that says, well, maybe it's a bit disguising if the only actual component that changes over time is the carbon emissions. Why don't we just use carbon emissions? It's more tangible. And on the other hand, it's a very important measure, because it's good to aggregate all these different components into one single measure to say something about the sustainability at the overall level. So it's a bit a tricky balance to find right. I think for scientific reasons it's better to use the environmental footprints, because they can be easily quantified and replicably estimated, and they're very specific, right? So we have one footprint for carbon, we have one footprint for land, so they really help assessing environmental and sustainability challenge in a very tangible manner. But when it comes to communicating sustainability or the lack of sustainability from a more aggregate perspective, then it can definitely make sense to use the ecological footprint. But again, it's always important to understand what the ecological footprint actually is and how it relates to the underlying environmental footprints. In the last part of this lecture, I want to give a little outlook on what can be done or what other challenges we face when we want to tackle the problem of environmental and social unsustainability. Here is a plot again for carbon footprints in Germany, and we can do similar things in other countries. So we see that carbon taxes are regressive. What does it mean? A regressive tax is a tax that is less severe as people get richer. So how come? In this plot, there's again two values plotted. We have first in the background these big bars with the light colors. This is the carbon footprint of different income groups. And it's sorted by income groups, so we have on the left side the low income groups and then on the right side the high income groups, and each income group has a certain share of the population. Like this income group here has an average 2,700 euros per month, and it's like 15 million people in that group. And it has a certain carbon footprint. And of course, with higher income, the carbon footprints rise. So this is what you can see here. There's a trend upwards in these background bars. And this is a common phenomenon, right? As we have seen before, as people have more money available, they spend more and they tend to have more higher carbon footprints. And we can look more into detail how much it actually increases. Is it a one-to-one increase or is it lower? That depends, of course, on the actual commodity composition we have here. What we can do in the second step is we can calculate, okay, let's assume there's a global carbon tax. In this setting, we had a 50 euro per ton carbon tax, and assume that the carbon tax applies economy-wide and quantities don't change. So people just continue consuming, so they have to pay the carbon tax. And what happens then is that the low income groups here, they would have a certain consumption. So it's about 7 tons per capita. And this would correspond to a certain carbon charge due to the tax. And this again, due to their income, which we also know, would account for roughly 2.5% of their total spendings. So the lowest income group would pay 2.5% of their income in the carbon tax, assuming that nothing else changes. And the highest income group, because simply they have more money and on average buy less carbon intensive products, they would spend less than 1% of their money in the carbon tax. And this is what we call regression, right? People get richer, so the relative tax load gets smaller. And this is a consequence of the fact that the basic needs, electricity, food, and transport, are the ones that are also carbon intensive. So there is really a good illustration of the entanglement we have between basic needs and the fossil fuel economy. So when we apply a carbon tax like this to the economy, it's basically an engine for more social inequality, because the low income groups get taxed highest. So we need to find schemes that redistribute some of the tax load to actually also, from a fairness principle, charge more money from the high income groups. This example here is a good illustration of the tight coupling between environmental policy and social policy. In the future, we need to think the two together. We cannot just devise instruments to tackle environmental sustainability, like reducing carbon emissions. We at the same time need to address the social aspects of such measures. Or more general, we can say that a wide range of sustainable development strategies needs to work together. So the economic incentives, the legal regulations, technology and lifestyles need to be integrated. And policymakers have the task of including the complexity of the system into their thinking as well. So when we do environmental policy, we also have to assess their social consequences and try to align social policy and climate policy and other environmental policy in the future, for example. We also see from our work that technology-mediated efficiency and lifestyle-mediated sufficiency need to work together. Neither of them is enough to reach substantial emissions reduction. Efficiency can get us very far, but it doesn't solve the whole problem. We also need to rethink our attitude to consumption and to the necessity of the services that we consume. But sufficiency alone also doesn't work, because in the current system, a climate sufficient lifestyle would be a very depressing lifestyle, because you can't do very much with the resources and the emissions budget you have. So we need both. We need a system change, for example having more efficiency, but we also need an individual change, a lifestyle change. One good pattern to illustrate this is the so-called avoid, shift, improve framework that has been mostly used in transport policy design, but that can also be used in other contexts. So avoid is again the lifestyle thing. Is it possible for you to avoid a certain service if you realize it's actually a luxury consumption and it's actually unfair, given that we burden a lot of impacts to future generations and we deprive poor people in our country and from this planet from also using the resources that we are currently using? So avoid starts at the individual level. And the shift improve options are at the systems level. So shift means if the system, for example the city, gives you different transport options, or there's different housing options where you can live more energy efficiently. So shift means you still consume the service, but the mode of service provision is different. And then of course in the individual stocks and products that provide the services, we can have a lot of improvement. We can shift from gasoline vehicles to electric vehicles. We can make buildings more energy efficient. So this all would be improve examples. And they three together, so avoiding consumption, shifting the mode of service provision, and improving products and devices, can help to have a major cut in environmental impacts, but at the same time reaching very positive social outcomes. And this avoid thing is a new strand of research, because predominant research doesn't like to touch the idea of individual freedom and freedom to consume, but we realize, especially in higher income countries, this doesn't really work in the future. We face so severe environmental crisis that we really need to rethink our attitude to service consumption and consumption in general, and this then links scientifically to the question of so-called demand side solution. So not just supply side, meaning renewable energies and new products, but also questioning and redesigning the way we consume products. And on this slide, I leave it to you for reading. There's a number of instruments that we can use to foster and study demand-side solutions, and also a couple of research questions that can be studied in those areas. So the vision that we would develop is the vision of the donut economy, or a bit simpler drawn on the right side, the vision that economy is not in itself a column of sustainability or a pillar of sustainability. It's rather embedded. It's embedded in the social objectives and the environmental objectives that we need to reach. And in the donut we have a more specific drawing. Again, we have the different planetary boundaries that are the environmental guide rails for our economic activities, and in the middle we have the social objectives that we need to reach to have a healthy and prosperous society. A big question here is of course the fairness principle, including the question whether value chains emissions can be actually allocated to final consumers. But here again, a statement that just because your product carbon footprint is so and so high doesn't mean that you're responsible for all these emissions. Of course, the responsibility is a shared one between you as a consumer and the countries and industries where the emissions actually occur. In the first step, the carbon footprint and other supply chain based measures are indicators of how many emissions or other resources can be attributed to a person. But attribution and responsibility are two different things. And to resolve the question, and this is now the closure of this lecture, to resolve the question between individual responsibility and system-wide change, we need a very profound, a very deep reflection and also transformation process in the future. It is clear from industrial ecology research that we will need both. We will need to address private consumption, we will need to think about avoiding and about different ideas of how to provide human well-being and participation, but we also need systemic change. We need to address the energy system, the infrastructure, and of course the framework. And the idea is that both of them will work together. Only private consumption doesn't work. It will in most cases lead to depression if you throughout your whole life have to fight a system that doesn't want to change. Only systemic change doesn't work if the individuals continue to demand high impact products. So there needs to be a synergy between both sides, the individual private consumption, well-being and participation side, and the systemic energy supply and infrastructure supply side.